Okay, we come to the last class of this mini course. I had a good time. I hope you all did as well. So, we're going to look at representation learning, the third module, and we're going to see how we can use again different kinds of neural networks to learn representations, some of which are tailored for text, some of which we have to sort of modify for text. So, let's get started. Today, we're going to look at three main approaches. One is using adversarial networks, the next one is graph embeddings, and the next one is debiased embeddings. After these three, we'll wrap up the course with the limits of deep learning. And in the next hour, we'll discuss more open things like how to read research papers or what how basically how to approach research because when I was in my undergrad I had no idea what research entailed, and when I started my PhD right after, it was like deer cotton headlights, and any freewheeling questions, what you have felt about the course and so on. So it's a very I hope it's a very interactive session. So let's get started. So first, there's a very popular network called GANs. I won't be going into the mathematics of any of these techniques because the idea is to give a high level representation, just like we've done in the last two representation learning modules. So these are generative adversarial networks. Now, the philosophy of this is derived from both variational autoencoder, Siamese networks, and many other things actually. But from variational autoencoder, what we get is a kind of generative model. And from a Siamese network, what we get is a sort of discriminator model, both of which are present in a GAN. So that's what I've mentioned here, that we have a generative model and a discriminative model. Now, in machine learning, you might have learned that you have a difference between a generative and a discriminating model. In a generative model, you're trying to model the underlying data itself, but in a discriminator model, we're only trying to model the boundary between classes and so on. Now, interestingly, GANs have both a generative and a discriminative power. So let's see how that works. So, in a generative adversarial network, the idea is that yes, we will be learning a generative model. However, we also want to guide it towards uh, the task at hand, say classification. So, that is the adversarial part. In Siamese network, we saw a sort of adversarial training where we took pairs of dissimilar things that were put far apart. So we have the generative and the adversarial, and of course, the network stands for deep neural networks. Now, why go for this? Why do we just not use a deep neural network? The advantage of this is because if we have a generative model, we can generate new images or text that we had not seen while training. And we use this in variational autoencoder where we modeled the distribution by generating the mean and the other parameters of the assumption of the underlying model. So, this fact of robustness or generalizability is what makes generative adversarial networks very popular. Now, this is the architecture. So, you have real world images or text of which you take a sample and you feed it to the discriminator. On the other side, you have a generator which will generate the sample. Now, the discriminator here is going to decide whether this is real or fake, in the sense whether they are similar or dissimilar, quite similar to the Siamese network we had seen last class. And this is the loss function we have. Once again, we are going to do back propagation. So this is a random input we are generating, and it gets better and better as we propagate the errors back. So here we have the generative aspect, and here we have the discriminative aspect, and they actually are very powerful. So how do we train this? Initially, we lock the weights of the generator and we train the discriminator. So there are some weights, and we simply use the discriminator to show whether pairs are real or fake. Now, in the generator phase, we have already trained the weights of the discriminator, so we simply update the weights of the generator. Now, as you can imagine, this has to be done in an iteration, because the very first time there will be nothing generated, and so on. So this happens in an iterative process, and we train the discriminator and we train the generator again and again and again. So how can we improve this? So if you have image, for example, instead of using simply fully connected feed forward neural networks inside the discriminator, inside the generator, we can use convolutional networks. Now, these convolutional networks can be applied for either text or image, but as we have seen in the previous classes, image is most likely to be modeled with a convolutional network, and text is most likely modeled with LSTMs or by LSTMs and so on. And we can plug and play with any of the architectures we've seen so far. And these are more technical details which will make sense if we do the math, but I won't be doing that here for lack of time. So, what makes generative adversarial networks very interesting? Just like how we saw in the word embeddings task, we get a lot of useful semantic information in the vectorial representation. So, these are images that are generated by the generator, and if we see the space and sample images, we get very interesting patterns. So, this is from a text to image data set, and man with glasses, whatever was generated, when subtract with man without glasses, and then you add woman without glasses, the generator did come with woman with glasses. So it is a sort of two-layer learning, like it learns from the image as well as the text. So I think that's very fascinating, and this is the kind of power you can achieve with variants of the GAN model. And taking GAN itself properly would take around, like, I don't know, maybe 3 or 4 hours, because it's quite involved and it's very interesting. And of course, it is going to be the power of the data finally that's going to create such interesting patterns. I'm showing this here to sort of indicate how good the generator becomes over various iterations. This is again an example of the faces dataset, which was pioneering in the Siamese network space, that the generator model is able to do this on its own. So in Siamese network, if you remember, we need to bring some kind of augmentation, and this does not require that. So, this is an example of text to image synthesis. So, given a text description, we generate images closely associated. So, these days in social media, we actually see this happening. When your image is not loading, it gives you a sort of text description. And these have been done using deep learning, if not GAN. And what we do is literally the same thing. And in here there's a bit more complex layers, because it's not just text or image, we are using both. So we'll see how that works. So the generator network has uh, basically it's going to generate images, and the discriminator network is going to no, the generator network generates both the image and the text, and the discriminator network suggests whether it is correct or wrong. So it's like real image, right text, and the negative examples are real image, wrong text, fake image, right text, and so on. So we have the sense of positive examples, negative examples in the generator and discriminator network. So you can see it's as powerful as we saw sequence models, where you can use different modalities of data to generate useful information. Now, what are the advantages of GAN? We have seen in the last few representation learning modules that we've seen Boltzmann machine, again a generative model, variational autoencoders, again a generative model. What is it about generative adversarial networks that gives it an edge and makes it perform so well? First thing is the generation is straightforward. In variational autoencoders, it only generates the parameters of a function, and we have to sample from that function. Boltzmann machine, for example, we first of all, there was no error to estimate in a Boltzmann machine, and we had to somehow update the weights using convex optimization methods or approximations of the same. So that's the next point, that the training doesn't involve maximum likelihood estimation. You might have seen this in your machine learning course. It's basically an approximation of the generative space. Training of GANs, for example, uses the advantages of backpropagation in itself. It's robust to overfitting because the generator never sees the training data, and that is extremely unique to GANs. And empirically, which means we have seen this only in experiments, we don't know the mathematical backing of this, that GANs are good at capturing the modes of distribution, which is basically where you peak in the vector space. Now, what are the problems? One of it is non-convergence, because we are training the generative model and the discriminative model in a lot of iterations. And if we don't start at a convenient place, we might never be able to bring the random sample close to the actual um, real input. So that is the problem with non-convergence. So you can imagine that's because in the generative space, this is something completely random that we are trying to force by the generator to create a useful sample. Now, if this is not chosen properly, and this varies from input to input, we might never be able to push this sample close to the real image. So that is the problem of non-convergence. And though the fact that the generator does not see the text, I'm sorry, the fact that the generator does not see the input is an advantage and it is robust to overfitting. It is also a disadvantage in the sense it leads to non-convergence. The next problem is mode collapse. Mode, as I said before, is that they are good at capturing modes of the distribution. However, it's also it's related to other problems in deep neural networks, where you have like all these uh, um, different and complex type of text, that it is very they sort of tend to overlap and useful information is not obtained. So yes, this is up to the generative adversarial networks. We'll now be moving on to the graph embeddings. Now, why do we need graph embeddings, especially when I've been talking about text the entire course? But that's because text can be represented using graphs. Knowledge about domains can be represented using graphs. And embedding graphs in a useful way for neural networks improves our performance significantly. So, what is a graph? You might have learned this in your course on data structures, where you basically have two components, vertices and edges. And a graph uh, is well described by that. They can be either directed or undirected. And similarly, depending on that, we need to modify our network a bit. And the vertices are often called nodes. So you have the idea. And the input to your graph embedding model is going to be the adjacency matrix. As a recap, it just says whether um, node I and node J are connected. If it is undirected, I and J will have a value, and so will J and I. And if it is directed only in one direction, we will have the edge value. Now, this is the definition of a graph, and we have associated problems, which are the node classification problem, graph classification problem, and link prediction problem. In node classification, we see what are the types of nodes. In graph classification, as the name suggests, we see the type of graphs. And in link prediction, we see the idea between the edges, basically, the nodes, and say what type of edge it is. Now, when we study graphs, we don't really label the edges. In data structures and algorithms, for example, we use weights. But you can imagine in real world setting, the edges often have a type, and we want to predict what that type is. For example, in a dependency parse tree, we have an edge between a noun and a verb, and we say that this noun is the subject that this verb is referring to. So that is a case of link prediction. We want to say in this graph, what does this link represent? So that is what we will be looking at. So, what do we need to do for neural networks? So, we need to encode nodes such that the similarity in the embedding space approximates similarity in the original network. Here, similarity could denote the adjacency matrix, could denote the labels of the edges. You get to decide what works for you. And the similarity idea we saw in word embeddings, we saw in CME's network, and it's basically the goal of representation learning that we want to make similar things close to each other in the vector space. So, this is one of the examples that what ideally we want to look at is that we have this set of graphs and we want to put close nodes closer together. Basically, if you clustered around this graph, you'd say that, okay, these belong to a class, these belong to a class, these belong to a class, these belong to a class. And note that, for example, if you just took distance, um, yeah, so these would be far apart and these are close together. And in the embedding space, we also want them to be close to each other. So, how does this work? We send in a graph and we try to reconstruct the graph. So, the input is not the entire graph, we input parts of the graph and we generate the entire graph. And then we push it on for, say, node classification, graph classification, or link prediction. So whenever classification is there, as we have seen so far, we use softmax. And here link prediction is basically similarity we are seeing. And here autoencoders were used. So this is sort of the overall general idea. Now, why graph neural networks? The first thing is the convolutional neural networks and the recurrent neural networks cannot handle the graph input properly because they have the notion of order or spatiality. But GNNs have a certain structure that we need to exploit. So here we need to ignore the input order of nodes. We can do that by shuffling different parts of the graph and inputting and so on. The second thing is it's guided by the graph structure. So since we didn't get into the math of this, the back propagation considers the graph structure, and they update the hidden state of nodes by weighted sum of the states of the neighborhood. Um, that's because of the way we will be sending in the graphs, where we don't send just the adjacency matrix of the entire graph, but we also send parts of the graph. The third advantage is reasoning, because we also generate graphs from non-structural data, and this is of course a more specialized application, and that's what like makes it exciting. So now coming to how graph embeddings are used in NLP, we have something known as an abstract meaning representation that can be converted to text. So now we can see nice ways of combining, say, graph and sequence for AMR to text, or basically because the input is graph and the output is text, it makes sense that it will be graph to sequence. SQL to text, which is reading your SQL inputs for databases and generating text, again a graph to sequence model. And then document summarization, because documents, as we saw very early in latent discriminant analysis, can be represented as matrix, and that matrix can be interpreted as a graph. Whether you use latent semantic analysis or whether you use just counts and frequencies, we can do document summarization as a graph. And yeah, these are just a few of the examples. You might even just augment your network using the various parser graphs of text along with your LSTM model of text. So quickly, I'll just touch upon the abstract meaning representation. It basically has a lot of semantics. So an sentence such as Ryan's description of himself, a genius, would be represented as person, describe, name, Ryan, and genius, and describes arguments are person and genius. Person's argument is name, name's value is Ryan. So there is link prediction, there is node classification, and yeah, so this is a very rich representation, and we want to convert this to text, basically get the sentence, or the more interesting task of the reverse, that given a text we want to generate the AMR representation. So this is important because sequence model, for example, will just flatten this input, and closely related nodes will become far away in serialization. And also, it makes no sense to represent this as a sequence, because though there is a notion of order information, um, there are orders which are sort of parallel in nature, and that is one of the advantages of graph embeddings. So once we have the uh, base layer of graph neural networks, we can have variants such as graph convolutional or graph recurrent, similar to GANs, which enhance the processing. Though, of course, we will end up with more parameters, and that is a trade off we always will have to do. Either we have more complex networks that can do better, or um, but that can do better only on the condition of more data, or we use simpler models with less data. We come to the last part of the embeddings before we move into the disadvantages of deep learning, which is basically day biased embeddings. Now, we have seen bias in the very beginning of this course as a sort of mathematical bias of the model. Now, in this case, I'm not talking about that bias. I'm talking about bias more from the perspective of ethics. That I want to say that, look, what if the fact that all our text is actually biased is going to affect? So, the idea is that bias is a product of human curated text resources, not only text, many resources. So it was found that word embeddings learn unfavorable relationships, such as man is to woman is same as doctor is to nurse. Now, two approaches are there. We can debias them while learning the embeddings itself or in post processing. Now, it's very interesting because these models form the basis of most of AI related products. For example, in resume selection for a job, if it is done automatically at the earlier stages using an AI algorithm, it might inadvertently pick up on biases, and that is why most companies have stopped using such products, and rather they just use it to sort of fill in, say, date of birth or straightforward tasks and not do more higher level cognitive tasks, because all of these are trained on word embeddings and word embeddings are biased. So we need to move towards a space where we don't have these biases. And that's a tall task because our text is biased, our input is biased. How are we going to force it through the machine to remove this bias? So this is a sort of involved task because we are looking at the algorithmic bias, we are looking at NLP, and we are also looking at explainability or interpretability, because if it is not interpretable, we will not be able to measure whether the bias has been removed or not. And so this is one of the examples between English and Armenian. So if you put in he is a nurse, she is an engineer, it gets reverse translated to she is a nurse and he is an engineer. You might have seen this all over on social media that such biases exist. I have seen this in, say, our local languages as well. So, why does this happen? What apart from, of course, the fact that the text is biased, you if you recall our word appendix class, it depends, of course, on the context and the co-occurrences, and he and she, if we see, so we see how uh, he occurs far more in engineer than in nurse, far more in leader um, than in nurse, and pretty, for example, occurs a bit more than nurse for the he she co-occurrence. So, and apart from all of these he she differences, the fact that he dominates most of the text, that is also a red flag. So, and here it's the context window is 8, so it's pretty much um, expansive. And the other problem, of course, is that these are languages where the pronoun is not gendered. So that's another reason why such translations occur. So, coupled with the bias, the language structure also brings in some problems in modeling text. So, this is one of the ways of measuring bias, which is famous, which is that you use your information on what could be possible biases, which is basically like targeted word sets and attribute word sets, and then you see your particular word, how far it is from these values, and then you see how much bias is there. It's quite a simple method, and this gives you a measure for bias. Now, how do we remove bias? One idea is that you remove the vector relating to gender from all the embeddings. So the word gender would have an embedding, and not only the word gender, but synonyms of it, words close to it, will get a vector, and you subtract that vector from all the embeddings. So you subtract that vector from the vector for doctor, you subtract that vector for nurse, and so on. And then when you repeat these experiments, you will see that such associations do not crop up. So that is an advantage. When we subtract from the embeddings, we still mm, capture information about the meaning of the word, and we are just removing the component of that embedding. Now, this gives us the desired result, but it also chops off useful and required gender differences. So, the current research in this field is how do we balance both? We need the good biases, we don't need the harmful biases. Otherwise, it will just become completely non gendered, and what we want to go towards is that gender is a spectrum. We don't want to make it that gender is absent, and that is a very hard task. Finally, we come to the drawbacks of deep learning. Before I'd like to move on, I want your opinions. What do you think are the drawbacks of deep learning? Okay, I'll start presenting then. Um, as I suppose, like I have uh, presented a lot of deep learning networks, and it might be quite hard to like abstract from that. But generally, I'd like to discuss overall what are the drawbacks of deep learning methods. First thing is, we have only scratched the surface in the sense, um, if you see the success of it, they often happen in application oriented spaces, and we don't have a robust mathematical model, unlike in machine learning models. And when you experiment with it, as I'm sure you've seen it in the coding assignment as well, it's not a magic pill solution. The merits of deep learning is in two ways. One, it generalizes from a large set of unlabeled instances with few labeled instances. And as we saw in the very first class, that poorly described feature sets perform automatic feature extraction so that the domain expert need not spend hours collecting the features, annotating the data set, and so on. So, deep learning does well in places of ill defined schemes in terms of images or text or audio or speech. So, these are things that we don't know exactly how to represent. As a child, when we learn language, when we identify images as belonging to a class or the other, we just take two or three examples and we learn it, but we don't know how we are doing that. So these are things, since we don't know how we represent, it makes sense to use deep learning. However, deep learning does not give much of an advantage when the data set is small, say between 100 and thousands, and that I have seen in a lot of real world applications where we don't have much data. For example, in the biomedical field, or even text where the domain is very niche. Now, if your dataset already has features that have been extracted with a rich sense of domain knowledge, there is no point in using a general method such as deep learning to go forward. And if there is a large label dataset again with good features, it is better to go with machine learning methods than deep learning methods. We come to the first serious problem. So these are sort of like I was pushing towards where deep learning is useful, but now we come to actual problems of catastrophic forgetting, for example. So imagine if I see 1,000 pictures of dogs and then I see 1,000 pictures of cats. I will not forget the knowledge of recognizing dogs. However, if a deep neural network is developed on one task, that is of identifying dogs from other animals, and then overwritten, as in you train over it, and uh, then there is catastrophic forgetting because I only now know how to recognize cats from other animals. So there's no notion of memory. As in, I spent so much time learning one particular task, and now I'm saying a highly related task. So I should not have to do it from scratch. I should not have to have a data set that has both. There must be something while training, because training is a costly process. What is it that I will have that makes me mimic this human behavior? The next thing is this how we learn? Do we see thousands and thousands of pictures before we have a notion of what a dog looks like? We might spend a lot of time and understand how to behave with a pet or how to take care of a pet. But to just recognize whether an image is a dog or a cat, we do not need such a large data set. So, what is it in this formulation that we are missing out, that we're not getting the human behavior exactly? Now, let's look at other broad level concerns. The first one is the environmental concerns. Training is costly. Often it uses a lot of GPUs. For example, GPT-3 that we saw in one of our lectures um, has a model of more than a billion parameters, and it took far more data to process it. And not only is it time consuming, it is also a high environmental concern. The heat generated apparently is unbelievable. And after all that effort, it still has these drawbacks we talked about. So, that is one thing current research is looking at. How do we make these algorithms more efficient, that we don't have to use so much of computing power? In the beginning of the class, I started off telling it is the advancement of computing power that has made deep learning possible and powerful. But then there's also this drawback, that where do we stop? Yes, it's powerful, but do we go all out and just collect as much data as possible and literally fry the resources? The next problem, of course, is bias, which we touched upon briefly, but it is very crucial because a lot of applications are based on AI today. The third, and this is one of the biggest problems of deep learning, it is the lack of interpretability. I don't know why my model is behaving this way. I only know it is a magical black box that takes the input and gives me a beautiful discriminatory model. Now, for example, I'm currently working in the medical domain. I have this model that has generated a beautiful discriminatory idea and has brought out classification. Great. But on the other hand, I need to be able to tell a clinician, I want you to look out for this particular feature, and then I want you to use that for classification. And this is something I simply can't do in deep learning because it's not designed for that. So, lack of interpretability is a huge problem. Similarly, in the education domain, say when I'm working with word problems, if it is not interpretable, if I just have, say, an equation and um, I don't know how that equation has been generated, if I want to develop a program that will correct students' mistakes, I have no model to do that. Of course, for the fact of lack of interpretability, there are a lot of workarounds where you generate the problem itself to have some sense of interpretability. For example, explanations for word problems can be modeled with language, but these are all kind of roundabout ways, and we're trying to use the features extracted themselves to have a bit of interpretability. The fourth one is the data acquisition bottleneck, where this only works with large sets of data. and that is going to be hard, and it does not model our way of looking at things. So there's a gap there. The last one we'll be seeing is memory thrashing. You might have seen thrashing in the operating systems course. It's basically the same thing, where the deep learning model has to keep the entire thing in main memory to compute the distances, and that's a challenge for mobile devices. Most mobile devices which use apps that are based on deep learning often have the model on the server and just collect the input and output across internet. Or if it is offline, they have a very simplistic version of the model that can mimic the input and the output. So these are the kind of uh, drawbacks of deep learning. And what we want to move towards is efficient algorithms, understanding of both biology and computation, interdisciplinary research, modeling memory of human beings. So, actually, in the classical AI part, there was a lot of focus on memory. In fact, some of the algorithms that focused on memory is what later evolved into the OOPS concepts of class, inheritance, encapsulation, abstraction, and so on. All of that has some notion of memory. You're saving variables, there is a state, there are registers, and so on and so forth. Deep learning has no notion of that, and that is a bit of a concern. The last one, of course, is hardware improvements so that we don't have to fry our resources. So, thank you. I'm done with the lecture today.